Okay. Good morning, students. In last class about 16th group elements introduction and electronic configuration, some important properties, physical properties and anomalous properties of 16th group elements. Then variable oxidation states of 16th group elements. After anomalous properties of oxygen and some important properties like chemical properties, variable oxidation state by oxygen, sulfur, selenium, tellurium and polonium. Next important topic is chemical properties of 16th group elements, that is reactivity towards hydrogen. Okay. Here 16th group elements are denoted as symbol E. They are oxygen, sulfur, selenium, tellurium and polonium. So, polonium is a radioactive element. It is. These two are the non-metals. These are metalloids. It is a radioactive metal. These 16th group elements react with the hydrogen. Okay. Then 16th group elements react with hydrogen. It forms H2E type hydrides. H2E type hydrides means your hydrogen is common. Your element oxygen, sulfur, selenium, tellurium, polonium changes. Now here the H2O, this is the element. This is hydrogen, this is called hydrogen oxide. Hydrogen oxide. Your H2S, this is hydrogen sulfide. Hydrogen sulfide. Your H2SE, H2TE and H2PO. These are hydrogen selenoid. Selenoid this is. Your hydrogen telluride. This is polenoid. Hydrogen polenoid. These are the some important hydrides of a 16th group elements of the type H2E type. Now this hydrogen oxide, another name is water. This is universal liquid water. That H2O, name is here water, universal solvent. This is many important uses are there. And in first PUC, in 11th standard, about hydrogen and its compounds clearly explained about water, hard water and soft water, temporary and permanent hardness, how to purify this hard water. Anyhow, on the basis of all these hydrides of 16th group elements, H2O, H2S, H2SE, H2TE, H2PO, some important points about these hydrides of 16th group elements. They are maybe useful for objective or for theory, increasing order or decreasing order. Already in 15th group elements explained, hydrides of 15th group elements like ammonia, phosphine, arsen, stibin, bismuthine, some important hydrides explained. Similarly, your first one is your H2E. E is the central element of this hydride. Either maybe a oxygen, sulfur, selenium, tellurium or polonium, whatever, right? Here it is a 16th group element. that a 16th group element contain 6 valency electrons. Among the 6 valency electrons, here on central element E, 2 are the lone pairs, like 2 are the lone pairs, and remaining 2 are the unpaired. These unpaired electrons bonded with hydrogen covalently. Here the 2 sigma covalent bonds are present. And here the 2 lone pairs are there, LP. These 2 are the bond pair, BP. We know in chemical bonding, repulsive forces, that is lone pair repulsions are greater than lone pair bond to pair, then bond to pair and bond to pair. Based on valence shell electron pair repulsion theory, one of the most important forces, lone pair repulsions are more than compared to the lone pair bond pair, lone pair and bond pair, than compared to the bond pair and bond pair. So anyhow, here in this H2E type molecule, central element either oxygen, sulfur, selenium, tellurium and polonium undergoes sp3 hybridization. Okay, why it undergoes sp3 hybridization means, like this is E, here are 2 lone pairs are there and 2 are the bond pairs. So hybrid orbitals are for neutral molecule, lone pairs plus bond pairs. 2 plus 2, 4 are there. That's why sp3 hybridization. So in all hydrides of 16th group elements, central element undergo sp3. According to hybridization concept, if element undergo sp3 in any molecule, generally it shows tetrahedral geometry. But in this case, based on their these repulsive forces, even though it undergo sp3 hybridization, its geometry is not tetrahedral, its geometry is angular shape, because here there is a LP and BP repulsions are there, repulsive forces are there. So here the due to these repulsive forces, bond angle and geometry change. That's geometry is angular geometry, angular in shape, and here bond angle BA is generally decrease. In this case, less than 109 degrees 28 minutes. So that is commonly 104 degrees are there. 104 degrees 28 like R5. So depending upon this element, if it is oxygen, if it is sulfur, if it is selenium, tellurium and polonium, its bond angle changes. Geometry is same, for all this geometry is same, angular only. But here bond angle changes from oxygen means oxide to the polynoid, water to the polynoid, hydrogen polynoid, its bond angle changes. Why its bond angle changes means bond angle BA bond angle decreases. Why are the bond angle decreases? Because because size increases, size of the element increases, that's why your bond angle decreases. So by using all these, whenever this size increases between central element and hydrogen, bond length also increases. Here the size, for example, hydrogen size common in all the cases. Your hydrogen size is common, this is, but this is the oxygen. Hydrogen is common, this is sulfur. Hydrogen is common, this is selenoid. So year to year distance, what happens? Increases. So this is hydrogen and oxygen, hydrogen and sulfur, hydrogen and selenium, and so on. Top to bottom size of the central element increases, bond angle decreases because repulsive forces decreases. Lone pair, bond pair, repulsive forces decrease, bond angle also decreases. Whenever oxygen, sulfur, selenium till top to bottom atomic number increase, size increase between hydrogen and oxygen, length increases. When our bond length increase, these are loosely bonded. Attraction is less. They are ready to break up hydrogen, ready to produce H plus ions. That's why based on this structure, we can manage some important points for objective as well as for theory based on their structure and bond angle and repulsive forces. Your first one is about bond angle. So the bond angle is more in H2O than compared to the your H2S, than compared to the H2SC, than compared to H2TE, than compared to the your H2PO. This is here 104 degrees 5 minutes nearly, here 90 degrees. So total year to year bond angle decreases. So approximately here 98 degrees, 92 degrees, 91 degrees. Like here bond angle water to the like polynoid, hydrogen polynoid bond angle decreases because size increases. Generally, it is a radioactive element. Generally, we can consider up to here. Anyhow, we are given in our textbook this H2PO also. This is the bond angle story. When our bond angle is like decreases, immediately bond energy, dissociation energy, that is in kilojoules. Here instead of bond energies, I'll take bond length first. Bond length is in picometers. So the bond length between oxygen and hydrogen, sulfur and hydrogen, selenium and hydrogen, what happens? Bond length increases. That's why symbols are H2O, like less than H2S, less than H2SE, less than H2TE, less than H2PO. When our bond length increases, bond distance increases, bond energy, bond dissociation energy, bond enthalpy also, bond energy in kilojoules. Here H2O is more because bond length is less. To break that, more amount of energy required. That's why H2O is greater than compared to the H2S, H2SE, H2TE, H2PO. This is when our bond energy is more, means dissociation bond energy or bond dissociation energy. Bond dissociation energy is more, cannot easily produce H plus ions. That's why removal of hydrogen is not easily takes place. That's why those who are readily produces H plus ions, according to Arrhenius theory, when dissolved in water it produces H plus ion, that is acidic in nature. Similarly, this hydrogen in water, hydrogen cannot easily produce because more amount of energy required to break a bond. Attractive forces are more because bond length is less. That's why here reducing nature is least for water, highest for that H2T or H2PO, because reducing means ready to produce H plus ions. That's why the H2O is less than, H2S is less than H2Se less than H2Te less than H2PO. This is same here. The reducing nature is more, same acidic nature also. Yeah, the acidic nature also same. So reducing nature as well as acidic nature both are same. Then next one is here your boiling and melting points. Here sixth one is melting points and boiling points. Generally, your melting and boiling points are more for this water molecule. More for water molecule means your originally H2S is less than, H2S is less than, H2T is less than H2O. This is very, very important. Now your water has highest your boiling and melting points. Reason behind that, in water and particularly in this H2S, there is one good reason is there. Here intermolecular hydrogen bonds are present, here weak van der Waals forces are present. Due to this reason only, your H2O exists as a liquid, whereas H2S exists as a gas. In NCERT book, in text questions, your why H2O is a liquid in nature, H2S is a gaseous in nature. Reason is behind that, due to the presence of certain bonds. They are in water molecule, intermolecular hydrogen bonds are present, whereas in H2S there is no such intermolecular hydrogen bonds. Very, very important. I'll show that how it forms intermolecular hydrogen bonds. Here water molecule H2O we can take like, and another water molecule we can take like, another water molecule like we can take in first PUC in 11th standard explained about the structure of water, that is in liquid state as well as in solid state. In liquid state, around one oxygen atom, your three bonds are present, hydrogen bonds. Two are the sigma covalent bonds and one is with dotted line. This is a hydrogen bond, HB, that is intermolecular hydrogen bonds, not intermolecular hydrogen bond is present, because that dotted lines means here electrostatic force of attraction exists between hydrogen and highly electronegativity of oxygen or fluorine or nitrogen. So our hydrogen bond is between hydrogen and highly electronegativity fluorine or oxygen or nitrogen. Between these three elements only form. Not chlorine, not sulfur, not any phosphorus, like there is no hydrogen bond. So here in one molecule, water molecule, oxygen atom, and in another same molecule, hydrogen, in water hydrogen, this is the hydrogen and this combination is exist in water. That's why it is a intermolecular hydrogen bond is present between two same or the different. Like it is a cyclic process takes place, continuously takes place. Due to the presence of this, a strong electrostatic force of attraction exists to vaporize here at room temperature nearly at atmospheric 100 degrees Celsius required, or 273 kelvins, 373 kelvins required. It's boiling point of water. Due to the presence of this intermolecular hydrogen bond, they are not easily vaporized. Volatile nature is less than compared to this H2S, H2Se, H2Te. So boiling and melting points are more for water than compared to other. That's why instead of we can write first, last we can write. This is more increasing order. So here, due to the presence of this more boiling point, not easily volatile. Not easily volatile means cannot easily evaporated from its surface. Only it reaches above 100 degrees Celsius, water is ready to vaporizes. Above 100 degrees Celsius, these intermolecular hydrogen bonds are ready to break up. Cleavage takes place, then easily vaporizes. That's why in the month of May, April and May, temperature increases, atmospheric temperature increases. Water present in a full swimming pool or any river, water easily dry rises temperature. Bonds are ready to break layer to layer. Water evaporated. Only it's above 100 degrees Celsius or 373 kelvins. Whereas in case of H2S, your hydrogen sulfide, like hydrogen sulfide, there is no such a sulfur and hydrogen intermolecular hydrogen bond. Here there exists a weak van der Waals forces. So due to the presence of this weak van der Waals forces, they are easily evaporated from the surface of this H2S. That's why it is in gaseous state exists. So our gas to slowly, gaseous nature decreases, liquid and solid nature increases. These are the some important points about hydrides of 16th group elements, that is reactivity towards hydrogen. Clear points? So first, on the basis of structure, number of lone pairs and bond pairs, hybridization, bond angle and bond length. On the basis bond angle and bond length, we can manage all these points. Better you read from textbook. In textbook, not given this clear information, just as given a theoretical explanation and one table created by using the table. Better you read. Okay. Next, the second important thing is next, second important chemical properties, reactivity towards oxygen. So in reactivity towards oxygen means here 16th group element, first element itself oxygen only. Oxygen combines itself, it gives corresponding oxides. The 16th group elements are generally here oxygen, sulfur, selenium, tellurium and polonium. These are. So these elements combines with oxygen directly, it forms corresponding oxides. These corresponding oxides are generally two types. These two types are generally EO2 and EO3 type. Now this EO2 is nothing but it is a dioxides, and here EO3 is nothing but it is a trioxides. So are the 16th group elements forms generally when it combines with oxygen directly, it forms dioxides and trioxides. Now here dioxides EO2 and trioxides EO3. I'll create an important table. So here dioxides and in trioxides, Your oxygen is the first element, combines with the oxygen, it forms OO2 like this. Yeah, the oxygenated oxygen dioxygen that we can take as a O3. That O3 is a ozone molecule. Then your sulfur combines with oxygen. Your element sulfur, it gives SO2, sulfur dioxide, oxygen dioxide it is. Now here the selenium dioxide, SeO2. Your tellurium oxide, TeO2, tellurium oxide. Your polonium dioxide, that is. Now here the EO3 means oxygen again do not combines with here the 3 moles of oxygen. Do not. There is no such a trioxides with the oxygen. Sulfur combines with oxygen, sulfur trioxide. Your selenium combines with oxygen, selenium trioxide. Tellurium trioxide, here also do not. These two are not possible. Why it is not possible means oxygen trioxides means that is absence of d orbital. The reason behind that here oxygen do not form trioxides. Here due to the inert pair effect, due to the inert pair and pore shielding effect, polonium also, even if it forms not stable. So these are the two important oxides of 16th group elements. On the basis, yeah, some important points are there after these chemical properties. So the story about O3 is there, SO2 is there, SO3 is there, all the points are there, dioxin also there, I'll explain all these. Before that, here trioxides are more acidic than dioxides. That's why here EO3 are more acidic than compared to EO2. Very, very important. On the basis, your SO3 is highest acidic oxide. It is among the 16th group elements. Now its acidic strength is SO2 is greater than SeO2 is greater than TeO2. Similarly, your trioxides acidic nature is SO3 is greater than SeO3 is greater than TeO3. This is the order of this acidic strength of dioxides and trioxides. Now here the SO2 dioxide acts as a reducing agent. Reducing agent. That reducing agent means your oxidation reaction takes place. Oxidation means ready to convert dioxides to trioxides. Now here the tellurium dioxide acts as a oxidizing agent. Oxidizing agent that is ready to produce oxygen. That's why here in this table among all the types of oxides, very, very important story about SO2 and TeO2 and SO3. So are the more acidic oxide, and trioxides are more acidic than compared to the dioxides because higher oxidation states compounds are more acidic than compared to the lower oxidation state. Then comparing all these, SO3 is more acidic in nature. Then among these three, this is the highest. This is the among these some dioxides, SO2 is more acidic in oxide. Now it acts as a RA reducing agent. It acts as a OA oxidizing agent. These are the some important points about oxides of 16th group elements. That is reactivity towards oxygen. Table very, very important. Better you take one rough notes about this oxygen. Reactivity towards oxygen. Next one is reactivity towards halogens. Reactivity towards halogens. Your halogens are X 17th group elements like fluorine, chlorine, bromine, iodine. Astatine is a radioactive element. This is in atomic state, in a molecular state, that is AF2, Cl2, Br2, and I2. These are halogens, 17th group elements. Your elements are here. E elements are oxygen, sulfur, selenium, tellurium, and polonium. These are the 16th group elements. These are 17th group elements. Generally, these 17th group elements, 17th group elements are generally having high electronegative elements than compared to these 16th group elements, generally having less electronegativity nature. So on the basis, these 16th group elements combines with the 17th group elements, it forms like generally EX type, that is monohalides. These monohalides dimerize, it gives E2X2 type. Like means monohalides, dihalides, trihalides, and hexahalides. These are the some important halides of 16th group elements. Very, very important. So are the generally these hexahalides, tetrahalides, and dihalides important. These are the monohalides. On the basis of these chemical reactivities and electronegativity characters, here stability of different stability. Here the stability of halides. These halides, 16th group halides stabilities are generally F minus is greater than, Cl minus is greater than, here Br minus is greater than I minus. This is very, very important. So stability, which halide is more stable. I'll take one simple example. SeEF6 is there. Here SCl6 is there. SBr6 is there. Si6 is there. This is stability order. Fluoride, chloride, bromide, iodides. Sulfur hexafluoride, sulfur hexachloride, sulfur hexabromide, sulfur hexaiodide. So among these stability, in this case, chlorine is fluorine is -1, chlorine is -1, Br -1, I -1. So among these F minus compounds are more stable, means SF6 is more stable than compared to the SCl6, than compared to the SBr6, than compared to the Si6. And now textbook given only one word, like hexafluorides are more stable, exceptional. That is, it is more stable. It is more stable. Reason is due to steric repulsive reasons. Steric repulsions reasons, these are more stable. Among all these, sulfur hexafluoride is more stable halide. Now in first PUC in chemical bonding explained to you, it do not obey the octet electronic configuration. More than 8 electrons are present. Around sulfur, here sulfur, 6 valency electrons are there out of 6. In excited state, 6 fluorine atoms are bonded like. Here the 6 fluorine atoms are bonded. In its outermost orbit in ground state, two only unpaired, remaining four are paired, but excite the electrons from lower energy level to the higher energy level. Reason is due to the presence of d orbitals in its outermost orbit, excite it forms six covalent bonds. Six covalent bonds mean the sulfur undergoes sp3d2 hybridization. sp3d2 means it is generally all hexafluorides, hexalates having generally octahedral structure, octahedral geometries. Like we can take like this, hexafluorides. So here the EX6 type generally having sp3d2, like 6 sigma covalent bonds are there, sp3d2 octahedral structure, that is EX type. Generally here OF6 do not. Why oxygen do not form OF6? What is the reason behind that? We are concentrating only on sulfur and selenium, not on oxygen. Reason behind that, here OF6 is not possible. Here the OF4 also not possible. Only here OF2 is possible. It is possible. Only around oxygen, here only two unpaired electrons are there which are react with fluorine. Remaining two are lone pairs present as these. But these are not possible. These are not possible because here to get the 6 and 4 bonds compulsory we want d orbitals. That's why absence of d orbitals do not forms OF6 and OF4. Hexafluorides, tetrafluorides of oxygen are not possible. Only OF2. Already given in oxidation state, in this case, oxygen exhibit +2 oxidation state because it is -1. -1 into 2, -2, it is a +2 oxidation state. That's why OF6 and OF4 tetrafluorides and hexafluorides of oxygens are not possible. Reason behind the absence of d orbital. Whereas in other cases, sulfur, selenium, tellurium, polonium form such a different fluorides like hexafluorides, tetrafluorides, like difluorides, monofluorides. This is a story about hexafluorides. Sulfur hexafluoride, sulfur hexachloride. Among all these, more stable is this. If they will give an examination, objective examination now, yeah, these related compounds are more stable. Which is more stable means, for example, in examination, if they will give like SF6, your SAF6, your TF6, like POF6, maybe it will ask. Which is more stable? SF6. Reason is iodides are stable and small in size. Due to the steric repulsive forces, it is a stable fluoride. Remaining are stability decreases. Least stable is PO, not exist due to the inert pair effect. Story about hexafluoride, hybridization and geometry and structure and availability and stabilities of these. Now hexafluorides completed. Then tetrafluorides, tetrahalides. Here, after this hexafluorides, next one is tetrafluorides. Generally, oxygen do not possible. OF4 is not possible. Your SEF4 is possible. Your SEF4 is possible. Like TF4, like POF4 is possible. More stable is this stability. Or maybe your SCl4 or SBr4, like Si4 compounds are, but among these more stable compound is this. Now it is like this model. Around the element E, yeah, the 6 valency electrons are there. Out of 6 valency electrons, 2 are the unpaired electrons and remaining 2 are the pair, lone pairs. Now here the element is S maybe. Now here for total here we want 4 fluorine atom, 4 single electrons are required. That's why its electronic configuration is generally NS2, NP4, and your ND is there here. Now here the 2 electrons are there, here 4 electrons are there like this. Now this is vacant. Now here only 2 fluorine atoms are reacts in ground state, but we want 4 fluorine atoms. That's why here to here excites. Then here we'll get 1, 2, 3, 4 fluorine atoms are reacts. That's where the first excitation takes place. Then here it gives only 1 lone pair, and remaining 2 are the remaining 4 are the unpaired like this. Lewis dot structure. On the basis here the sulfur, it forms with this fluorine 1, with this fluorine 1. Now here 1 is lone pair it is, and this is again fluorine this is. Now here the sigma bonds 1, 2, 3, 4 and 1 lone pair. That's why here it is LP electrons. Total here sp3d. 1 sulfur, 1 s orbital, 3 p orbital and 1 d orbital is involved. That's why it is sp3d. It is a trigonal bipyramidal structure originally. This is also considered as a very important seesaw structure, very important. Now here 5 bonds are there. Among these 5, 2 are the axial bonds. These are the axial bonds. In equatorial, these are the axial bonds, but these are the equatorial bonds. In this equatorial bonds, 1 lone pair is there at equatorial position. At equatorial position, 1 lone pair is there. Due to the presence of this lone pair at equatorial position, lone pair and bond pair repulsions takes place. Its geometry same trigonal bipyramidal takes place, considered as a seesaw-like structure. So here the tetrafluorides, tetrachlorides, tetrabromides, tetraiodides undergoes trigonal bipyramidal seesaw structure, that is due to the presence of 1 lone pair. Clear? Its geometry and types of bonds, axial and equatorial, just like in PCl5 already explained to you, phosphorus pentachloride explained in 15th group elements, Cl, like 5 Cl atoms. Among these 5 bonds, 3 are the equatorial, 2 are the axial bonds, same as these bonds here. Okay, the next one is dihalides. 16th group elements, dihalides. Yeah, generally dihalides means here EX2 like this. OEF2 also forms due to the presence of due to the absence of d orbital cannot excite. On oxygen atom 2 lone pairs and 2 are the unpaired, yeah, fluorine and fluorine, but due to the presence of these 2 lone pair repulsions takes place. Generally it takes place angular shape like this, angular in shape like. So the angular means nearly bond angle is 120 degrees or 120 to 130 degrees based on the central atom of an element. Now here SF2, here SEF2, here TEF2, your POEF2. These are the dihalides. In dihalides, central atom of an element undergo your sp3 hybridization. Like, see here, your SF2 is there. Around sulfur, here the two lone pairs are there. Like, and two bond pairs are present. Sigma bonds are 2 and lone pairs are 2. These two are the lone pairs. Now hybridized orbitals are here 2 plus 2, that is 4. So hybridization is sp3. If it is sp3 hybridization, then geometry is tetrahedral, but not tetrahedral. Why are they? In this case, your sp3 hybridization, if it is sp3 hybridization, geometry is tetrahedral originally, only tetrahedral if the central metal do not have any lone pair or without any LP electrons, it shows tetrahedral if it is sp3. That is AB4 model in chemical bonding explained to you. Now, if it is AB to E2 model example, this is means two lone pairs are there. That is ASF2. Here it contains two lone pairs. Then its geometry changes to a tetrahedral to a angular shape. That is due to the lone pair and lone pair, and here lone pair and bond to pair repulsions. This is lone pair, lone pair, lone pair and bond pair repulsions. Geometry also changes. Even though in this type also it undergoes sp3 hybridization. sp3 geometry is not tetrahedral. Only sp3 AB4 type without lone pair, sp3 tetrahedral. Your AB to E2 model containing two lone pairs, sp3, but not a tetrahedral, it is a angular shape. The reason is lone pair and lone pair bond pair repulsions. Then last one is monohalides. Important monohalides. In our NCERT book, last one line given, monohalides are dimerases and are easily undergo disproportionation reaction. Very, very important point that is. So the monohalides means, for example, EX. If we can take EX like SF, if we can take, yeah, around sulfur 6 valency electrons are there out of 6. One fluorine is bonded with one sulfur like this, but one is unpaired is present. This is monofluoride, sulfur 1 and fluorine 1. But this is eagerly waiting to react with other molecule. That's why one more sulfur and fluorine. Here again sulfur and fluorine again eagerly waiting. Then monofluoride and monofluoride. Sulfur monofluoride dimerizes. These two are mutual contribution, mutual sharing takes place. It forms 7 covalent bond. This is the dimeric structure. So are the monofluorides are the dimerases. Then it forms like S2Cl2, like SeCl2, are the TCl2 like R S2Br2, are Se2Br2, Ta2 Br2. These are the some important examples. They are dimerizes easily. Now, in this case, due to the presence of dimeric structure, even it contains a lone pair of electrons and also pairs are there. Generally, these are having linear geometry. This is around sulfur 4 bonds are there, 2 lone pairs, and these 2 are the sigma bonds. sp3 hybridization in a dimeric structure, linear in shape. Now, these monofluorides are easily disproportionate. That disproportionation reaction is your Se2Cl2, here the 2 moles. On disproportionation, it gives SeCl4. plus 3 Se is formed. See here, in this case, minus 1 into 2, minus 2, this is the plus 1 oxidation state. Now, here to here, oxidation state is plus 4. What happens? Plus 4 increases. Means removal of electrons takes place. Removal of electron means positive charge increases. Oxidation reaction takes place. The same selenium, here to here, it is a 0. So here the plus 1 to 0 means positive charge decrease, negative charge increase, means here the reduction reaction takes place. So in one compound, the selenium undergo both oxidation as well as reduction reaction. That's why it is a disproportionation. Here the disproportionation reaction takes place. Very, very important reaction it is. Finally, for objective in first PUC, one of the most important question is there mustard gas is there. Di 2-chloro-ethyl bromide or sulfide like mustard gas. One chemical reaction given, not given in our NCERT book. Anyhow, better you note on this point. Mustard gas formula is here S2Cl2 is reacted with CH2 double bond CH2 like 2 moles. It gives here the Cl bond CH2 bond CH2 taken twice S plus S. It is a mustard gas. Here around sulfur 2 bonds like CH2 CH2 bond Cl, then here CH2 CH2 Cl. Now this is central element sulfur containing 6 valency electrons out of 6, 2 are bonded with this, 2 lone pairs are there, and again it is sulfur precipitate is formed. Now here in this compound 2 chlorine atoms are there, di. That's why we can take di bracket 2 ethyl dichloro 2 ethyl sorry di 2 chloro ethyl sulfide. This is di means 2 are there, dichloroethyl sulfide. It is a mustard gas. Very, very important formula this is. Like Cl, CH2, CH2 taken twice and Es. So these are the some important points about chemical properties of 16th group elements, like reactivity towards hydrogen, reactivity towards oxygen, reactivity towards halogens. Halogens are very, very important. Then tomorrow I'll discuss about compounds of 16th group elements like dioxygen, ozone, simple oxides, and about ozone molecule and sulfur compound, sulfur dioxide, sulfur trioxide, and sulfuric acid. Maximum Friday, Saturday, 2 days. Within 2 days, I'll complete this unit. Very simple unit. Okay. Today only better you complete all this. Okay. Take care. Thank you.